We've talked about conformational energies of alkanes. Now let's look at cycloalkanes. And we're going to look at 4. We're going to look at cyclopropane, a 3-carbon ring that's supposed to be connected. We'll look at cyclobutane, a 4-carbon ring, cyclopentane, and if you haven't guessed what the last one is, it will be cyclohexane. So here are 4 molecules. We've drawn them flat. Why do we draw these flat? Because we're writing on a flat surface, and so that's convenient for us to draw in that way. However, representing these as flat may or may not be an accurate representation of what they really look like. So if you look at all these carbons, what we'll find is all these rings contain sp3 carbons. So we think the ideal bond angle for all these carbons should be 109.5. However, if you go back to your high school geometry class and look at what the internal bond angle is for these polygons, you'll see that for cyclopentane, it's 60 degrees. And for a flat structure, for cyclobutane, it's 90. For cyclopentane, it's 108. And for cyclohexane, it's going to be 120. So, as you can see, these molecules, if they are flat, are going to have bond angles that are very far from the ideal state. And that gives rise to something called angle strain. If you get deviations from the ideal bond angle, you get angle strain. So that leads to a consequence that these structures may be unstable. So we're going to look at the total strain, total energy, total strain energy in each one of these 4 structures. And these are going to be in kcals per mole. Now this total strain is not just angle strain. There are many things that give rise to strain. We've already seen there could be torsional strain. There could be steric repulsion, and there's not a lot of steric repulsion in these structures, but certainly there's some torsional strain. And then finally there's this new idea of angle strain. So what's total energy of these structures? Well, cyclopropane is indeed a fairly unstable structure. It has a strain energy of 27.5. And we don't have a lot of perspective to know, is that a big number, is that a small number? 27.5 is a pretty big strain. Cyclobutane, the angle strain should be much less in cyclobutane, but you have four internal angles that are distorted, not just 3 as in cyclopropane. So actually cyclobutane is still up there, about 26.3 kcals per mole. Now, as you get to 108 in cyclopentane, you might think this number ought to go down. This ought to be a much more stable structure. And it is 6.2 kcals per mole of calculated strain energy in that structure. And then cyclohexane, you think, wow, this number ought to go back up because now, instead of being too small, this bond angle in cyclohexane is too big. So what's the strain energy of cyclohexane? It's actually 0.0. And so what this tells us is this representation, this flat representation, is not accurate for cyclohexane. Somehow cyclohexane is adopting an ideal bond angle, even though we wouldn't predict it from the flat structure. So cyclohexane is not flat. Actually, the only one that is flat is cyclopropane. Cyclobutane and cyclopentane are a little bit distorted. They are not perfectly flat, although personally I consider them to be pretty flat. But cyclohexane is a special case. It is definitely not flat. And so we'll need to talk about how you draw cyclohexane properly to represent the fact that it is not flat and has actually fairly close to ideal bond angles of 109.5.